Today we're going to be reviewing the Calc Med Unit 3, and we're going to be talking about derivatives, specifically implicit differentiation. We've talked about derivatives last time, product rule and chain rule. Implicit differentiation is necessary when the function doesn't necessarily pass the VLT. Okay, and it's difficult to express the function in y equals notation. So when do we use it? When the curve fails the VLT or is difficult to express as y equals. So it's hard to get y by itself. So what are the steps then? So leave the equation the way it is and take the derivative of both sides. So you want to take the derivative of the left side and the derivative of the right side with respect to x. You have to remember to apply the chain rule to all the terms that are all the variables in terms of y. So anything that has a y on it would also have the chain rule of dy dx. Then you want to gather all the dy dx's on the left side. So all the dy dx terms you want to collect together. You want to factor that expression. So factor the left side. And then you'll use division to get dy dx alone. And that's implicit differentiation. So let's take a look at a couple sample problems that use implicit differentiation. All right, so this is a kind of an ellipse, and it's going to fail the vertical line test. And it's also difficult for us to get y by itself. So we're going to take the derivative of both sides. So the derivative of x squared is 2x. The derivative of 4xy needs the chain rule. So that'll be needs the product rule. So it'll be x times dy dx plus y times dx dx, which happens to be 1. Derivative of y squared. So that will be minus 2y, and then chain rule again, dy dx. And the derivative of the right side, because 7 is a constant, is 0. So now we want to distribute our 4, and then that will allow us, and simplify here, and that will allow us to gather all of our dy dx terms on the left-hand side. So we'll have 4x dy dx, and the other dy dx term is minus 2y dy dx. But to the other side, we're going to kick over that negative 2x, and we're also going to kick over negative 4y. So now we'll factor, and we'll be left with 4x minus 2y inside the parentheses. And then we can divide. So I'm going to divide, and we'll have 4x minus 2y. And I'm going to reduce everything by 2 just to simplify. So we're going to have negative x minus 2y over 2x, and then minus y. And that is my derivative in terms of x and y. All right, let's do another one. Here's a natural log function that also has a cubic, so it's not going to pass the vertical line test, and is virtually impossible for us to get y by itself without using the cubic rule, so we don't want to do that. Let's just apply implicit derivatives. So the derivative of y cubed, 3y squared times the chain rule of dy dx, and then the derivative of 4x is 4, and the derivative of the natural log is 1 over y times the chain rule of dy dx again. So we want to gather our terms. So 3y squared dy dx minus 1 over y dy dx equals negative 4. So then I can factor out my dy dx term. So let's pull dy dx out to the front as we're factoring it, and then I'll erase this. We can just write it as our expression. And then we can divide. So dy dx is negative 4 over 3y squared minus the fraction 1 over y. Now it's kind of awkward to write it like that, so if we multiply every term by y, then we'll have negative 4y in the numerator. That will give me 3y cubed, but it'll allow me to have minus 1. That's just a cleaner way of writing it, so you don't have a fraction within a fraction. Now we're asked if the tangent line to the graph could be horizontal. So that means that our dy dx, which is negative 4y over 3y cubed minus 1, if it's going to be horizontal, it's got to be equal to 0 over 1. So if we cross multiply that, we're going to have negative 4y equals 0. In other words, y equals 0. Let's look back at the original equation, and if I try and put 0 into a natural log, that's not part of the domain. This is not in the domain of our original question. So there is no point where the tangent line to the graph would be horizontal, so that would be your explanation. The only point that it might be falls outside of the domain. Therefore, there is no possible point where the graph of the tangent line to our curve would be horizontal. All right, and then last, write the equation of a tangent line. So we know we need the point and we need the slope. Now we know y is 1, but how are we going to find x? Well, we're going to plug y is 1 back into the original function. So we'll have 1 cubed plus 4x equals the natural log of 1, which is 0. So 4x equals negative 1. So x has to be negative 1/4. And then the slope, dy dx, we'll use our derivative. So negative 4 times y, which is 1, over 3 times 1 cubed. So we have negative 4 over 2, so negative 2. So overall our tangent line is y minus 1, negative 2 for the slope, and then x plus 1/4. And remember, we talked about yesterday, you don't have to waste your time simplifying. That is a valid answer. All right, so exam tips. What can we learn from today? One is that we can find horizontal tangents when we set the derivative equal to 0. So we want to solve dy dx equal to 0 over 1. By the similar vein, vertical tangents, you can find those when you set the derivative equal to 1 over 0. So we would, I meant to write solving there. So we would write dy dx equals 1 over 0. So those are some AP exam tips to pull away. Once you have the expression of a derivative, you're going to cross multiply to find the places where it might be horizontally or vertically tangent.